All right, let's dive straight into this explainer and discover the totally fascinating geometric rules that govern how lines interact with circles. I mean, if you've ever watched a bicycle wheel rolling down the street or a belt turning on a car's engine pulley, you've actually witnessed the precise, invisible mathematics we're going to unpack today. In this explainer, we are completely focusing on the core concepts of this geometry chapter, breaking down exactly how straight lines interact with perfect curves.
To make sense of all these ideas, we're going to follow a really quick roadmap. First, an introduction to tangents. Second, the radius relationship. Third, tangents from the outside. And finally, putting theorems to work to solve some actual puzzles.
So, Section 1, Introduction to Tangents. Let's get our absolute basics down. To get us in the right mindset, I want you to just imagine a straight line moving steadily toward a circle. You kind of have to ask yourself about the precise moment they first meet, right? Like, does the line cross right through? Does it miss entirely? Or does it do something mathematically unique?
Well, this brings us to two very distinct definitions you absolutely need to know. On one hand, we have what's called a secant. A secant cuts right through the circle in two places. Think of an arrow passing straight through an apple. But on the other hand, we have our star player, the tangent. A tangent perfectly grazes the edge, touching the circle at exactly one unique spot. It doesn't cross the boundary, it literally just elegantly kisses the edge.
You can really visualize this exact progression. Think about a line starting out completely missing the circle entirely. Then, it shifts a bit and slices through 2 points, creating our secant. Finally, it shifts just enough to become a tangent, intersecting at that one singular perfect point.
And that one hyperspecific spot where they meet, that is mathematically known as the point of contact. This isn't just some random dot. It is literally the anchor for every single rule we're about to learn.
And keep in mind, this isn't just abstract math meant to stay trapped in a textbook. The point of contact is exactly what allows a rope to seamlessly grip a pulley to lift water from a well. It's the exact physics of how your bicycle wheel smoothly rolls along the pavement without just sinking into the dirt. Literally, every time you ride a bike, the flat road is acting as a perfect tangent to your circular wheels. Pretty cool, right?
Moving right along to Section 2, the radius relationship, or as I like to call it, the 90-degree rule.
Let's see how this builds our first major proof, Theorem 10.1. We construct it step by step using the very simple logic of shortest distances. If we have a tangent line touching at a specific point, let's call it point P, and then we pick any other random point on that line, well, that new point has to be outside the circle. Because it's outside, the distance from the center of the circle to that new point is definitely longer than the radius. This completely proves that the radius line going to point P is the absolute shortest distance between the center and the tangent line. And a golden rule of geometry? The shortest distance between a point and a line is always a straight perpendicular drop.
So the conclusion is absolutely rock solid. The tangent at any point of a circle is always perfectly perpendicular to the radius through the point of contact. That 90-degree angle is a geometric guarantee. You can absolutely take that to the bank.
All right, Section 3, Tangents from the outside.
Let's zoom out a bit. We've got a simple rule of 3 here, which dictates exactly how many tangents are even possible depending on where your starting point is located. If your point is inside the circle, you get 0 tangents. Any line you draw will just slice right through as a secant. If your point is exactly on the circle's edge, you get exactly 1 tangent. But if your point is outside the circle, you unlock the ability to draw exactly 2 tangents.
So the crucial takeaway here is this. When you place a point completely outside the circle, you can draw exactly 2 distinct tangents touching the edges. This specific setup is the entire basis for our next major theorem.
Which brings us to Theorem 10.2. By just applying basic triangle congruence rules, we can prove something incredibly powerful about these 2 outside lines. When we draw those 2 tangents from our outside point and then connect radii to the points of contact, we instantly create 2 right-angled triangles. They share a hypotenuse, and obviously their radii are the exact same length. So, because of the right-angle hypotenuse side congruence rule, those 2 triangles are identical twins.
What's really wild about this is that because those 2 triangles are perfectly congruent, it means the lengths of the tangents drawn from that external point to the circle are perfectly equal. One line segment is exactly the same length as the other, always, no exceptions.
Okay, we have our 2 golden rules in hand. Now for the fun part. Section 4, Putting Theorems to Work. Let's see how these solve real geometric puzzles from our source material.
Imagine two concentric circles. That just means they share the exact same center point, kind of like a bullseye. Now imagine a chord slicing through the larger outer circle, but it just lightly touches the smaller inner circle. Well, from the perspective of the small circle, that chord is actually acting as a perfect tangent.
So, how do we solve things here? By simply remembering our very first rule. We know our radius hits the tangent at a strict 90-degree angle. And from basic geometry rules, we know a perpendicular line dropped from a center to a chord perfectly slices that chord in half. So boom, we immediately prove that the chord is completely bisected right at the point of contact. It's almost like magic how elegantly these rules stack together.
Let's tackle a slightly harder puzzle. Picture an 8-centimeter chord, a 5-centimeter radius, and we need to find the exact length of a tangent segment drawn from an outside point. At first glance, it looks like a mess of lines, but really, it's just a combination of our two golden rules. By throwing everything we've learned at it, the perpendicular radii from Theorem 10.1 and those equal tangent lengths from Theorem 10.2, we can easily establish similar triangles. Once you do the step-by-step math, you can confidently calculate the exact length of that tangent to be 20/3 centimeters. All that complex shape stuff just melts away when you apply the foundations.
And wow, that brings us to the end of our geometric journey. The math we explored today isn't just trapped on paper. It literally forms the invisible, structural framework of the physical world around us, from the wheels on your car to the pulleys in an elevator shaft. So I want to leave you with a challenge. Look around your room right now. Where can you spot these hidden geometric tangents interacting with the physical circles in your own environment? Keep your eyes open and keep learning.